Alrighty, so we're doing A3. We're graphing f of x equals ax squared plus bx plus c. So now we have the entire trinomial. And just note that this is our new introduction today, is that b of x term that we didn't have last week, right? And what impact does that b value make on our parabola? Okay, so the big thing here is when you have this bx term, okay, your axis of symmetry starts to come off the y-axis and it starts to move to different x values. It's no longer centered at x equals 0. Okay? And one of the big things that I want to point out is that as soon as that happens, I want y'all to notice that at that point, our y-intercept, which is c, is no longer the same point as the vertex. They are now two different points. Your vertex is still on the axis of symmetry, but that's shifted, so your y-intercept is a different point when that happens. So the y-intercept is still c, though. That's really helpful. Anytime you have your equation in front of you, you can always look right here at the end for your constant, and that immediately gives you probably the quickest, fastest point you can find on your parabola. Okay, but it is not always the vertex anymore. Okay. So now that our axis of symmetry is no longer always at 0, and therefore neither is our vertex, right? The question is, well, how do we find that quickly or easily? So the good news is that from standard form, which is what this up here is, ax squared plus bx plus c, that's what we consider standard form of a polynomial, and in this case a quadratic. Okay. We can use this formula right here, this x equals negative b over 2a, to always locate not just the axis of symmetry, right? It locates where the axis of symmetry is, but additionally it gives me the x coordinate of the vertex, because remember, my vertex is always on the axis of symmetry, so the x coordinate should always match the equation for that vertical line where my axis of symmetry lives. Okay, so is everybody okay with that part so far? Now, this is a fairly simple formula, guys. That negative b over 2a, all it needs is those two ingredients, a and b. A and b come from the standard form here. Here's my a. A is the coefficient in front of the x squared term, the degree 2 term. B is the coefficient in front of the linear term. Okay. However, I'm going to give you some words of advice on this. This is how the formula always comes. This is how you'll find it on the EOC formula chart, in the textbook, every book I've ever seen. However, in my experience doing this for many years, I have found that when my students use it like this, there are times, especially if you're a little still slightly shaky on your signs, on your positive and negatives, that having the negative out in front like this can be a little confusing. Okay, because what the reality is that in addition to the negative that's in front of this, A can also be negative and B can also be negative. So sometimes you've got not just this negative, but possibly one in the numerator and or one in the denominator. Okay, and if you're not really comfortable with juggling multiple signs and understanding what's going to happen in there with order of operations, that can be a cause of careless mistakes or just small errors. Okay, so what I have found is that it makes it a little bit easier to compute with, and it just seems to have a higher success rate. Okay, if you get into kind of the habit of putting that negative on the 2 instead. The reality is it's the exact same thing. Okay, the negative is still present, and mathematically speaking, it doesn't matter where we put it, if we put it out in front or we put it on the 2. I've always found it more successful in the long run, attaching it to that constant, the 2 that is always there anyway, and thinking of this as b over negative 2a. So you'll probably hear me say that a lot, but just know it's the same thing as the one that you might see in the book or on the formula chart, which is negative b over 2a, right? I just think that attaching it to the 2, all of a sudden the computation just seems to flow better for my students in that way and less mistakes. So that's just a little bit of food for thought there. They both work. Obviously, they're exactly the same formula. Okay, but as long as you know those 2 numbers from the standard form, you can find the axis of symmetry for your quadratic equation and also the x coordinate for your vertex, right? So that's kind of the big idea. In addition, though, if you find the full vertex, we'll also know what the max and min of our parabola is. So here's a slightly new vocabulary word, right? Where's our max and min? Right here, right? But it still represents just that vertex. So we already knew that the vertex was the highest or the lowest point on the parabola. Remember we had talked about that, right? So the y-coordinate of the vertex is always going to tell us what is the maximum value of that curve before it changes direction and comes back down, or what is the lowest point of that parabola before it changes direction and comes back up, right? So if A is less than 0, which is just fancy for negative, then we know that this is going to open downward like this, and your vertex is going to be a maximum. And the y-coordinate of your vertex is the one that gives away what is that maximum. Okay? And then if A is greater than 0, which is just fancy for positive, then it opens upward and our vertex is a minimum. Okay? So the real question when you're asked, does this parabola have a max or a min? That really is answered by the sign on A. Again, does it open upward or downward? That's what answers that question, right? Is what sign does A have? Because that then tells you which direction this opens, which then concludes on whether it's a max or a min, okay? Where it's located, what the actual value is, well, that's given by the y-coordinate of your vertex, all right? So again, and I've said this before last week, guys, but the vertex is a really information-rich point. Not only is it important in general to the parabola and usually very meaningful in word problems, but it also gives you some really good information because it gives you the vertex, right? But as soon as you know what this x-coordinate is, you know that's also your axis of symmetry equation. And as soon as you know what this y-coordinate is, you also know this is your either max or min depending on the parabola. Okay? So it's a very information-rich. Okay? So here's the fun part. The max and min is important, the y-coordinate. How do we find that? Well, remember, what a formula did we just talk about that helps us find the axis of symmetry? What's our formula for that? Boom, right? So this guy right here, we're going to find it every time from the standard form by doing our b over negative 2a, right? But here's the nice part. Remember, an ordered pair in a function situation like this, right? An ordered pair is a pair of input-output, right? So once this formula right here tells me what my x input is, what's the only thing I have to do to then find my y? If I know what x is, what do I do with x to find my corresponding y value? Plug it in, right? Exactly. Right, we plug it into the function, right? So now if I do my b over negative 2a, and let's pretend I get an x value of 3, and it tells me, okay, your axis of symmetry is a 3, that's your x input. And then I'm like, okay, well, but what is y? Well, all I have to do is take that 3 and plug it in and solve for that. And whatever that result is, that's my y output. That's my max or min, okay? So that's what we're going to practice on this one right here. So we have two jobs here on this first practice problem. First is find the axis of symmetry. Okay, so that's part A. And then the second one is whether or not, find the vertex, right? Which is just basically plug it back in and solve for y. So if I had to give you the steps here, for part A, axis of symmetry, this is going to be all about that b over negative 2a. That's how we're going to find for part A that axis of symmetry. Okay, for part B, to find the vertex, we are going to use, right, that b over negative 2a, or that x value, as the input. And solve for y. Okay, so that's for the second part there. I'm going to make sure I am on the thinner side here. Otherwise, it's going to be too thick. Okay, so let's start with number 1, right? So if I'm going to first find the axis of symmetry with that x equals b over negative 2a, I need to identify a and b. Okay, so I need to first find out what is the value of A here and what is the value of B before I proceed. So for number 1, what's our value of A? 1, right? So that's the coefficient right in front of that x squared. I don't see anything there. That automatically means that's a 1. What's our value of B? That guy right there is negative 10. That's B. As long as I have those two numbers, right, I can start doing part A here, which is finding that axis of symmetry with this formula of B over negative 2A. Right, so to find that, we'll plug in B, which is negative 10, over negative 2 times A, which happened to just be a 1. Okay? And then we just do order of operations there. So negative 2 times 1 is still negative 2, and then negative 10 divided by negative 2, positive 5. So guess what? We just found the axis of symmetry. We know that our axis of symmetry is located at the vertical line where x is always equal to 5. So I would go 5 units to the right, and I would make a vertical line there. That would be my axis of symmetry to this parabola. Where x is 5, yeah. Okay? And we'll graph a couple in just a moment. Okay. Now that we have this, though, now we go to part B, and we say, okay, well, they also asked us to find the vertex. Right? That basically means we already know the x-coordinate because we know that the x-coordinate of our vertex is exactly the same value as that axis of symmetry. So I already know half of my vertex point because it's got to be the 5 that I got for x in part A. The real question here is what's the corresponding y output for that, right? And so for me to find that, all I have to do is use 5 as an input in our function and solve. Okay, so I'm going to not grab this. There it goes. Okay, so I'm going to move that over, and I'm going to solve this f of x function that we had up here originally, but I'm going to use 5 as my input in particular, and I'm going to solve. So f of x is now f of 5 equals, and then I'll insert 5 for x here and say, 5 squared minus 10 times 5 again as my input, plus 2. And then you can either do that with just being careful with your order of operations. You can do that by hand, or you could use your calculator, but I'm going to highly, highly caution you. Anything that you put in the calculator that looks like this, you should be making sure you wrap your input with those parentheses. Put those parentheses around the 5 like I did here to make sure that the calculator does the correct order of operations also. Okay, so if we do that, what is 5 squared? Yeah, so we get 25 there. What is negative 10 times 5? Negative 50, right? And now we just go from left to right. So 25 minus 50, negative 25, and negative 25 plus 2, negative 23. So guess what? Right? The rest of our ordered pair is 5 comma negative 23. That is our vertex location. So we've got 5 here and negative 23 there. Okay. We could also just go crazy and say, hey, I also know that since A was positive, this opens in which direction? If A is positive, this opens upward, which makes negative 23 the minimum of this parabola. Okay? So we'll do a couple of practice ones, but that's really what you're doing. Okay? So that we could also even go as far as saying, I know that this parabola has an axis of symmetry at 5, a minimum value of negative 23. The vertex is at 5 comma negative 23. Boom, mic drop, right? Okay, so try number 2. Okay, so for number 2, first thing I want to do is identify what A value and what the B value is. So here A is what, guys? That's going to be a negative 4, and B is 16. Is that okay with everybody? I don't see a C value. What does that tell me about C? Yeah, and that's okay. That is okay. The first parabolas we explored didn't have a B or a C. Doesn't always have to have it. That just means it's 0. But we can still find, C doesn't really have a whole lot to do with us finding the axis of symmetry or the vertex, so we're all right. Okay? All right, so for part A here, we are going to first find axis of symmetry using our nice little formula B over negative 2A, which in this particular case means 16 over negative 2 times negative 4. Is that okay with everybody? Just insert that a and b in there. Okay, and then let's just simplify that. What's negative 2 times negative 4? That's going to be a positive 8, and then 16 over 8 just gives us 2. So it turns out that our axis of symmetry is at x equals 2. And that's kind of part 1 of the problem. Okay, so that's all done. And now we go on to part B, which is actually finding the rest of the vertex. We already know the x-coordinate has to be the same as the axis of symmetry, and we really just need to find what's the corresponding output, right? What is y when x is 2 in this function? Okay, now, Audrey asked a little bit ago, what can we use to table? This actually would not be a bad place. I mean, some of these I'm going to ask you to show your work, but if you were just doing it on your own, you could go now to the table and just look for a 2 and look for where the corresponding y output is 2, or at least check your work that way. So what we're going to do is we're just going to take our equation, y equals that negative 4, and we're going to insert 2 for x. So negative 4x squared becomes negative 4 2 squared plus 16 times 2. Right? So we're just inserting that specific x value where we know the vertex lives, and we're just simplifying that. So what's 2 squared? Okay, and then 4 times 4, right? Negative 4 times 4, sorry, is negative 16, and 16 times 2 is just 32, and then negative 16 plus 32 is 16, right? So our full vertex is going to be at 2, 16 for this particular one. Okay. And I should box my answer. Okay. All right, give me some thumbs up, down. How do we feel about those? So far, okay, yeah. No, that's a great question. Nope, it does not. Just as a side note, I could have a parabola that has a positive value that is both a max or a min, or a negative value that could be a max or a min. So where it's located vertically doesn't have to do with which way it opens. You could have both options. Yeah, so for that part, you really want to look at the sign on A. Mm-hmm. Okay. All right, any other questions before we move on? All right, I want y'all to try one more on your own. Or do you want to try one more? We're good? Okay, we're moving on. So you can always see those on Schoology. Let's go on to then graphing with this, which is kind of where we're headed, right? Graph the function and describe the domain and range. But to graph it, I want y'all to use this technique specifically. So I'm going to model what I'm looking for on tonight's homework, on tomorrow's quiz, on next week's test, like how I want you, because I want you to do basically what we just did, find that axis of symmetry, and then find the vertex, and then we'll talk about how to find a couple other points. So let's start with this one here. First of all, to graph, let's identify all three things, because we're going to need all three things this time. A, what is B, and what is C. So what is A here? 3. What is B? And what is C? 2. Okay? You might be wondering why we want 2, but I'll show you, or C, and I'll show you in just a moment. So we'll start off like we did a moment ago. First, we're going to identify where's our axis of symmetry located. Yeah. We don't, right, so that's what I was saying. You're going to want it now because it'll be a really easy other point to graph. We did not need it. We don't need C to find the axis of symmetry or the vertex. The reason why I'm identifying C is because after I find the axis of symmetry and the vertex, I'm going to want some other points to make my curve and graph it. And that is probably the easiest point to go jump on right there, because it's right there for me to just grab it. Okay? So that's why I'm using it now, okay, because I'm graphing. All right, so step 1, let's talk about axis of symmetry. So step 1, let's find axis of symmetry with our wonderful little formula, b over negative 2a. And in this particular case, b over negative 2a is going to look like 6 over negative 2 times 3. Okay? Is that okay? And negative 2 times 3 is just negative 6. And 6 over negative 6 is -1. Okay? So what that means is as I start to graph this, okay, I'm going to go ahead. Let's say that I make my grid right here. The way that I want y'all to show this, I'm modeling here, is you're going to make a dashed or broken line right here and you're going to label the actual equation of that line. So there's our axis of symmetry. That's what that would need to look like. Again, on tonight's homework, on the quiz, on the test, on everything, you're going to show your axis of symmetry as an imaginary dashed line, and you give the equation of that line. Okay? Now let's go ahead and take it a step further and find our vertex, right? So our vertex goes to what we did a moment ago, where we take this and we plug it back in. So now that I know that the x-coordinate has to be a -1, I take our original function and I plug in -1. Like that, okay? And I crunch that number either with a calculator or my amazing brain, right? -1 squared is still just 1. 1 times 3 is 3. -1 times 6, -6. And then we have that +2. And then -3 minus 6 is, I'm sorry, 3 minus 6 is -3, and -3 plus 2 is -1. So it turns out that my output is also 1. So my vertex, the entire vertex ordered pair, is at -1, -1. Okay, that's fine. So now I come here and I go ahead and plot that really obviously, and I just label that as our vertex so we know where that's located. Okay. Now this is what Campbell and I were talking about. A minute ago, all they asked us for was axis and vertex, and that was it. But now I'm graphing. That's not enough for me to make a parabola to kind of know how wide or narrow, which direction it's going in. So I need at least another point or two, right? That's where C comes in. So really easy. I mean, I could pick any point, but why do I do more work than I have to? If I know right off the bat that this constant on the end is always my y-intercept, okay, then step 3 is just say, hey, plot your y-intercept, and in this case, that's 2. So I can come right here and say, boom, I know that point right there is also on my parabola. It's just a quick, easy point to jump in. And then, here's the even better news. When it comes to parabolas, you always get a 2-for-1 deal. Buy one, get one, okay? So if I know that that's my y-intercept and that is located 1 unit to the right of my axis of symmetry, I know I have an exactly identical point 1 unit to the left of my axis of symmetry as well. So I can just reflect that and boom, we're in business right here, okay? I like to have 5 when possible, but some of these grow really fast. Really 3 gives you a fairly good idea of where this parabola is headed. So now we know that this is where our parabola is at. And there it is. Okay? And then the rest of it is fairly simple. What's the domain for all parabolas unless they're a word problem? All real numbers, right? So this is always all real numbers. And then what's our range? All the y values that are good, greater than or equal to -1, because that is the min of this curve. That is the minimum value of the curve. That's always correlated to that range. Yeah. The only time that the domain on a parabola is not all real numbers is if it's a word problem. If all of a sudden that x-axis represents, I don't know, time, for example, negative time doesn't make sense, right? So then we would start at 0 and go forward. So when it's in the context of a situation and that x input represents something real, like time or distance, things like that, then there might be some natural limitations to it. But in a problem like this, it's not attached to any real scenario. It's always all real numbers. Yeah, unless it's a word problem and you put arrows on both ends, just like I did. Just say, hey, I'm not going to keep graphing this forever, but it goes on forever, just like that, okay? All right, are we okay with that, with the graphing? Try number 6 if you have not already, okay? You're going to, things that I'm looking for credit are the axis of symmetry, marked and labeled, the vertex, plotted and labeled. The y-intercept also, and then reflected, right? And then the domain and range. Let's try number 6. Okay, so is that enough time? Did y'all get an axis of symmetry at 2? Good. What about the full vertex? 2 comma what? Negative 9. Good. So right here, so your axis of symmetry should be at positive 2 when you do the b over negative 2a. Remember, a is 2 here, b is the negative 8. Okay, c is going to be a negative 1. So when we plug that in to this guy, we end up with a negative 8 over a negative 2 times 2. Okay, that's going to give us a negative 8 over a negative 4, which is equal to 2. Okay, so that's our axis of symmetry. When you plug that 2 back in, right, if we come in here and we say y equals 2 squared minus 8 times 2 and minus 1, that should simplify to 9, but let's try it. What's 2 squared? 4. 4 times 2, 8. Okay, negative 8 times 2, negative 16, and then minus 1. And then we just go left to right. So 8 minus 16 gives us negative 8. And then negative 8 minus 1, negative 9, right? So there's our negative 9, which is the second part of that point, right? So right here at 2 comma negative 9, that's where my vertex lives. Okay, then I need another point. That's where C comes in handy because it's a really easy one. I could pick other stuff, but I'm not about to do more work than I need to if I can help it. Okay, so C equals negative 1. Right away, it tells me that this parabola intersects the y-axis right there at negative 1. And again, we always get a buy one, get one free here. If it's 2 units to the left here, I know I have an identical point 2 units to the right, so there's another point on my parabola right over there. If it helps, you can also plug in 1 and see where this is at 1. If you want to do that, you can do that as well. Okay, but right here, this gives us a good amount of time, points to kind of figure this out. Now, if I plug in a 1, that's going to be 2 minus 8. That's going to be a negative 7. So that would be right about right here. Okay, so that always helps a little bit. There it is. Okay, what's our domain? All real numbers. What is our range? Exactly. All the y values that are greater than or equal to that minimum of negative 9. All right, so are we feeling okay with the graphing part of it? Awesome. Okay, so let's go on to max and min. No different. The only difference here is that they're asking us if it's a max or min. So I had already hinted at that earlier, that what's really going to decide whether the function has a max value or a minimum value is the sign on A, right? What determines this is the sign of A, okay? That's what determines whether it's a max or a min, because that's going to determine if it opens upward or downward. What the actual value is going to be exactly the same process. We'll do b over negative 2a, we'll find x, we'll plug x in, and find y. Just like we did the whole time. Okay? So let's take a look at number 8, sorry. All right, I notice a is a negative 1/2. That means that a here is less than 0, or in other words, negative. Does that make this a max or a min? That's going to make that a max. Okay, so that answers question number 1 here. Okay, so if that a value is less than 0, which means negative, right, then we know we're looking at a maximum value. Okay, how to find it? Well, first we'll find x using our b over negative 2a formula. Okay, so for this particular problem, that means negative 5 over negative 2 times negative 1/2. This is the kind of problem that if we had the negative out in front, I feel like it might be a little confusing. But, just attaching it to the 2 seems to make it a little smoother. because this is not too bad. What's negative 2 times negative 1/2? 1, right? How nice is that? Right, so now we end up with just negative 5 over 1, which we just know is negative 5, right? And then that's not my max or min, but it tells me what I can plug in for x to find my y coordinate, which is my max or min. Okay, so now that I know that x is negative 5, then I come back in to the function and I plug that in for x. My max or min is the y value, so that's what I'm solving for now. Okay, whatever that whole string of computation is, that's my max for this one, for this parabola. Okay, so let's try that. Negative 5 squared is a positive 25. Okay, and then negative 1/2 of 25 is negative 12.5. By the way, negative 5 times negative 5 is also a positive 25 here. Okay, and then I'll combine these guys right here. That's a positive 12.5. Plus the 2 gives us 14.5. Okay, so our max is 14.5. That is the highest value that our parabola will ever reach. Okay, try number 9. And then raise your hand if you think you have it, and we'll check it. First of all, if this a value is 8, which is greater than 0, then is this a max or a min? It is a min, okay? And then we go through the process again. We use that b over negative 2a. For us, that means 16 over negative 2 times 8, which is just 16 over negative 16, which is just negative 1. Is that okay with everybody? And we plug that back in. So if we plug that back in, negative 1 squared plus 16 times negative 1 minus 2. That squared is 1 times 8 is 8. Negative 16 times negative 1 is negative 16. This right here is negative 8. And negative 8 minus 2 is negative 10. So our min is negative 10. All right? All right, then we're going to move on to the word problem and finish out with that. So the function h equals negative 16t squared plus 250t represents the height in feet of a rocket t seconds after it has been launched. The rocket explodes at its highest point. So that's just a kind of real world fancy way of saying at the max, right? The highest point of our parabola is going to be the max point, which is the vertex. So it's just in context of the real world way of saying, you know, the vertex and the max point. So when does the rocket explode? So when is talking about time, and time is my input. Okay, that's kind of the equivalent of x, right? So when does my rocket explode? We really are talking about the x coordinate of the vertex. Okay? Because that's our input, and in this particular problem, time is the input in the original function. Okay? So for that, all we have to do is continue using that b over negative 2a formula. And in this particular problem, a is negative 16 and b is the 250. So that's what I'm going to use in our formula when we plug that in for x. that's going to look like this. 250 over that negative 2 times negative 16. Okay? And that denominator simplifies to 32. And when I divide 250 by 32, I get 7.8125. Feel free definitely to do that with your calculator. Okay, so if we round that out, we can answer this question by saying that the rocket explodes about 7.8 seconds later, right? So we can say the rocket explodes after about 7.8 seconds. Okay. Part B says, at what height does the rocket explode? Well, that's just then asking us for the corresponding y coordinate. That's that. Let's try that again. All right. The y coordinate of the vertex, which will give us that max height. Okay. And to do that, all we have to do is take our original function, h, and solve it for when our time is at 7.8 seconds. So if we insert that 7.8125, because I like to be exact, right? I'd rather not use the rounded version if I can help it. And I insert that as my input time. I want to know what is the height when we were at this time. And then just crunch that out. Again, you can use your calculator. It turns out that that happens at 976.5625 feet in the air. Okay? And so the rocket explodes at a height of about, let's write that out. So the rocket explodes at a height of about 976.56 feet. Okay? So it's a real world situation that's really just still asking us for the x and y coordinates of the vertex, because that's usually when important things happen in a word problem.